arc length. In this section, we're going to see how we can find the arc length of a curve. And to find the length of a curve, the basic idea is we break the curve into smaller and smaller linear segments. We add up all of those linear segments, and we can use that as an approximation of the arc length. Well, as those linear segments get smaller and smaller, and we add up more and more of them, so as we let the number of segments approach infinity, this becomes an integral. And so what we can say is, if the derivative of the function is continuous on some closed interval ab, then it can be shown that the length of the curve y equals f of x on the interval from a to b is given by the arc length as the integral from a to b of the square root of 1 plus f prime of x squared dx. A couple of alternative ideas here. Instead of using f prime, we can use dy dx. And if instead of y being a function of x, if instead x is a function of y, then all we need to do is adjust our differentials to evaluate the integral and find the arc length. So let's see a fairly straightforward example. Here we're asked to find the length of the curve y equals 1/6 of x squared plus 4 to the 3/2 power on the interval 0 to 3. So notice in this we have y as a function of x. So what I will do is first calculate the derivative. So then dy dx would be 1/6 times 3/2 by x squared plus 4 to the 1/2 times, by the chain rule, 2x. So this simplifies as 1/6 times 3/2 times 2, that would be 1/2, times x squared plus 4 to the 1/2 power. Alright, so there's a little bit of side work for the derivative. Now, the arc length would be given by the integral from 0 to 3 of the square root of 1 plus the derivative of y squared. So we just found that derivative, so I'll use some brackets here. 1/2 x by x squared plus 4 to the 1/2, and that whole thing needs to be squared, and then with respect to x, we take that integral. So then the arc length is given by the integral from 0 to 3 of the square root of 1 plus, and squaring that quantity would give me 1/4 an x squared, and an x squared plus 4 to the 1/2 squared is an x squared plus 4. And again, this is all still with respect to x. Simplifying further, we'd have the integral from 0 to 3 of the square root of 1 plus 1/4 x to the 4th plus 1/4 x squared times 4 would be an x squared. Alright, now I'm going to rearrange the terms underneath the radical, giving me the integral from 0 to 3 of the square root of 1/4 x to the 4th plus x squared plus 1 dx. Now, remembering some stuff that I've learned from algebra, I notice that the radicand, what's underneath the radical, is actually a perfect square trinomial. And in fact, this arc length is equal to the integral from 0 to 3 of the square root of 1/2 x squared plus 1 quantity square. And when we take the square root of something squared, That gives us the absolute value of the quantity. But 1/2 x squared plus 1 is always positive, so we don't really need the absolutes here. And so I can just write that as the integral from 0 to 3 of 1/2 x squared plus 1 dx. And this is a fairly simple integral. So the arc length would then be, let's see, antiderivative of 1/2 x squared would be 1/6 x cubed, and antiderivative of 1 is x. And evaluating that from 0 to 3, or using a calculator, we get that the arc length is 15 halves. Now the TI-89 calculator has an arc length command on it, and we can use that to check our work. So let me bring up the calculator. And we want to do this from our graphing area. So I'm going to go into my y equals screen, and I have the equation set in as 1/6 x squared plus 4 to the 3 halves. And I'm going to now look at the graph in the standard window. So let me go to the graph. And so here's the graph. And if you go to the math submenu of the graphing feature, so under F5, if you scroll down for a while, you'll see an option for arc. Alright, so it's option B, and hit enter. And it now asks for a first point and a second point. So for the first point, you type in the x coordinate. So we were going from x equals 0 to x equals 3, so I'll type in 0, enter. And for the second point, I will type in 3, enter, and it will calculate the arc length, and we get 7.5, which is equivalent to 15 over 2. So I'm very confident in my analytical answer. So here's another example. Find the length of the curve y equals 2 natural log of sine of 1/2 x on pi over 3 to pi. So this would be a good one to try on your own. So if you'd like to, now would be a good time to pause. Alright, to find the length of the curve, again, since I have y as a function of x, the first thing I'm going to do is calculate the derivative. So then y prime would be 2. Let's see, the derivative of the natural log is 1 over the quantity, so that would be sine 1/2 x, times the derivative of the quantity, so that would be cosine of 1/2 x. Well, wait a second, we need a chain rule there, so times a 1/2. And so then simplifying, y prime, the 2 and the 1/2 multiply to 1, and I would have a cosine of 1/2 x over a sine of 1/2 x, and so that's equivalent to the cotangent of 1/2 x. Alright, calculating the arc length. The arc length would be the integral from pi over 3 to pi of the square root of 1 plus cotangent square of 1/2 x dx. Now let's see, 1 plus cotangent square. That is a Pythagorean identity from trigonometry. So integral from pi over 3 to pi of the square root of cosecant square x, not x, sorry, that should be a 1/2 x, dx. The square root of cosecant square, so integral pi over 3 to pi, absolute value of cosecant of 1/2 x dx. On the interval pi over 3 to pi, the sine, S-I-N-E, the sine function is positive, and so therefore the cosecant function would also be positive, or 0. It would never be negative. So I can just rewrite this as the integral from pi over 3 to pi of cosecant of 1/2 x dx. Now, I think I can evaluate this integral by using a substitution. If I let u equal 1/2 x, then du is 1/2 dx. So I would need a 1/2, and that would mean I would need a 2 outside the integral. So then the arc length would be twice the integral from pi over 3 to pi. And since I made well, it shouldn't be from pi over 3 to pi anymore because I changed the limit, I made the substitution. So u is 1/2 of x. So if x is pi over 3, u is pi over 6. And if if x is pi, u would be pi over 2. So twice the integral from pi over 6 to pi over 2 of cosecant u du. And cosecant, the integral of cosecant, we've seen this several times before. So the arc length would now be 2 times natural log absolute cosecant u minus cotangent u from pi over 6 to pi over 2. So the arc length would be 2 times, substituting the pi over 2. Let's see, we'd have the natural log of the absolute value of cosecant of pi over 2 minus cotangent of pi over 2 minus natural log absolute value cosecant pi over 6 minus cotangent pi over 6. So let's see, the cosecant of pi over 2, well, the sine of pi over 2 is 1, so its cosecant is 1. The cotangent of pi over 2 is 0. The cosecant of pi over 6, well, the sine of pi over 6 is 1/2, so the cosecant is 2, and the cotangent of pi over 6 ends up being the square root of 3. And we should be able to get all of that from, just our knowledge of the unit circle and trigonometry. So then the arc length is twice. Let's see, we would have the natural log of 1 minus 0 is 1, natural log of 1, minus the natural log of absolute value of 2 minus the square root of 3. Well, the square root of 3 is about 1.7, so 2 minus the square root of 3 is positive. So I don't need the absolute value there any longer. The natural log of 1 is 0, so that term goes away. And so I can write this arc length as negative 2 times the natural log of 2 minus the square root of 3, which is approximately 2.63 units. And again, we could check our work here on the calculator. Set up an integral that represents the length of the curve x equals y squared minus 2y on the interval 0 is less than or equal to y is less than or equal to 2. Then use a calculator to find the length correct to 4 decimal places. So notice here that we have x as a function of y. So we will want to find dx dy. Then dx dy would be 2y minus 2. So the arc length would be given as an integral from a to b of the square root of 1 plus dx dy square dx. I'm sorry, dy. So then the arc length would be the integral from 0 to 2 square root 1 plus dx dy we found earlier, that's 2y minus 2 square dy. So now I'm just going to use the calculator to evaluate that integral. All right, so I'm not going to actually use the arc length feature. I'm just going to go from the home screen and evaluate this integral. So I'll bring up my integral symbol, second, 7. There's my integral symbol, square root of 1 plus open quantity 2y minus 2 closed quantity square, close the radical, comma, with respect to y from 0 to 2. And we'll evaluate that. And we get some crazy number. All right, so this would not have been a very fun integral to evaluate. And let's find an approximation. So I'll hit green enter. And we get an approximation. It's about 2.9579 to 4 decimal places. The Gateway Arch in St. Louis was constructed using an equation, using the hyperbolic cosine for the central curve of the arch, where x and y are measured in meters and the absolute value of x is less than or equal to 91.20. We're asked to set up an integral for the length of the arch and use the calculator to estimate the length correct to the nearest meter. All right, so here we have y as a function of x, and we're asked to find an arc length, so let's calculate y prime. Y prime would be negative 20.96. The derivative of the hyperbolic cosine is the hyperbolic sine. So sine h of 0.032917665x times, by the chain rule, the derivative of that inside, which would be a 0.032911765. So there's our derivative. Now the arc length. Well, we're told that x varies as x is less than absolute x is less than or equal to 91.20. Recall that means that x is between negative 91.20 and positive 91.20. So I will set up my integral to go from negative 91.20 to positive 91.20. And for the integrand, I would have the square root of 1 plus, and I'm just going to write the y prime of x squared dx. All right, I've got that y prime from earlier. All right, and so now we would use the calculator, and so this is not fun to enter in the calculator, but if you do, you should get about 451 meters. All right, that concludes this presentation.